All right. Hi, everyone, and welcome to our session about machine learning-based diagnostics and analytics with application insights. Now, before we begin, let's do a quick raise of hands. How many of you are in the business of developing applications, operating them, managing them? Awesome. So I guess we're all in the same boat here. We can all agree that things are getting tough out there. Applications are becoming much more complex, and monitoring them and keeping their SLAs and SLOs are becoming an even more harder task. Now we have application performance management solutions, or APM solutions, to help it get crucial visibility into their performance and operations, but oftentimes these kind of solutions put the burden on us, developers and engineers and operations, to kind of keep tabs of what's happening, to pick up on issues ourselves, and kind of investigate issues as they happen. Now what we would really like is for these APM solutions to be proactive and to be smart. And by smart we mean that they will become aware of degradations as they evolve and before they become these colossal issues that all customers notice. And by smart, we also mean that they will help us do the root cause investigations of issues, essentially not leaving it up to us to sift through terabytes or petabytes of logs to find the needles in the haystack. And ultimately, we want them to be smart because we want to claim back our nights and our weekends, and we want to be carefree, even if we are the on-call team, knowing that our APM solution has our backs and will let us know whenever things go wrong with our service. Ultimately, this is where the combination between machine learning and domain knowledge come to our help and help us create better services that our customers enjoy and us as engineers are also happier, ultimately taking both of our experiences to new heights. Also, this kind of combination also helps us reclaim the position of the heroes of our applications. So I'm Ariel Breutman. Together with me is Yossi Atas. We're both from the Application Insights team. And in this session, we're going to talk about how the machine learning capabilities in Application Insights helps us and our customers essentially save hundreds of hours of root cause investigations and do things for us. Now, let's begin the Application Insights portal. Application Insights essentially is Microsoft APM solution for monitoring and tracking your applications and services. Now, for those not familiar with it, Application Insights is a comprehensive APM solution allowing you to get visibility into the health of your application, and with features like Application Map, where you can get visibility into your topology and the health of it, Smart Detection, which picks up on issues for you, which we're going to discuss in this session, Live Metrics Stream to get a real-time view of what's happening on your servers, Metric Explorer to slice and dice your metrics, availability testing with synthetic probes, failure analysis, performance analysis, etc. So one of the most common things we all do when we become aware of service disruptions is essentially go to a dashboard or some kind of report to look at the fail request or the exceptions, but eventually we all go pretty quickly to search. And the reason we go to search is because it's not enough just to know what the exception message is. We want to know all the things that characterize these exceptions. We want to know whether they're associated with a specific method, or if they evolve in a specific operation, or in a specific geography, or client OS, and etc. And essentially, there are so many properties for us to look at in these exceptions that it's making it super hard for us to know where to even begin. So luckily, Application Insights provide clustering of exceptions for us. It does so for all, essentially, telemetry data types, but we're looking here at exceptions. I see that I have, in the past 3 days, about 10,000 exceptions, which is pretty daunting, but essentially Application Insights broke them down into only 3 clusters of buckets. Now, these kind of buckets are super helpful because they provide me with the most prominent groups of exceptions with the common properties. So I know, for example, looking at this cluster, it covers about 16% of the exceptions. It's about 3.4K, and they all share the same operation name, so they happen all in the create service ticket operation. The message is that an error occurred, and I can drill in to see the exact message. All of them happening in a specific application version and a browser version, so that already gives me a good place to start my analysis because I know all the things that characterize this request. I can also drill in to see further details or specific instances of exceptions in that cluster. I can see the full error message, I can see the call stack, and I can also backtrack to see what happened as part of the operation which resulted in that exception being thrown. So in this case, let's see everything that happened from the bottom. So we see that a new request was received to the post service ticket create, so an attempt to create a new service ticket. followed by a SQL dependency call, which was successful to do a select. And that one followed by a failed SQL call to do an insert. And we see that the insert statement conflicted with the check constraint. So probably some kind of violation of primary key or foreign key in my database. And now that I got all this information, I know exactly where it happens. I know the flow. I can go ahead and look at my data access layer to know where should I fix it further. Now, this kind of magic of auto cluster happens by using an algorithm called seed expansion. That's a classic unsupervised machine learning algorithm. And essentially, application insight, when it applies it only to specific properties of exceptions in this case. So it knows just the most specific properties that will give you the most significant clusters. So this is where kind of the domain knowledge comes into play with the machine learning to produce the most meaningful clusters for you to investigate.
That's really cool, Arel. Sorry. Smart search is so important when investigating issues shortly after they take place. But as you noted in your intro, perhaps an even more powerful capability is to detect things before they turn into real problems. Let's move on to another capability that leverages machine learning and application insights. We call it smart detection. One evening in January, when I was the on-call engineer for one of the subsystems in Application Insights, I received an email from Application Insights notifying me about an evolving degradation in the duration of one of the HTTP operations in that subsystem. The email basically redirected me to this page. As we can see, Application Insight detected a significant increase in the server response time in that day, comparing to the normal baseline from the 7 days before that. It also showed me the number of users and requests that were impacted. Drilling into the analysis for this detection, we see a nice chart showing us the increase in response duration. And below that, we have a bar chart showing the daily loads on the system. As we can see, there were no major changes to the loads, so that rules out overload as a potential root cause. Below that, we see that Application Insights also detected a correlating degradation in the duration of one of the database calls that are triggered from the flow of the prolonging operation. That gives away the root cause pretty immediately. So Arel, Application Insight did not just detect an issue for me, it also helped me in triaging the issue, which is, in other words, to assess the severity, impact, and urgency of the issue, so I can decide, I can make an informed decision on whether I should deal with this right now, or it can wait until tomorrow morning. And on top of that, the service did most of the root cause analysis by surfacing the correlation between the degrading database call to the degrading HTTP operation. These kinds of detections are the results of pairing up machine learning algorithms together with domain knowledge and applying that to data collected from applications. That allows Application Insights to proactively look for a variety of application issues, and that's just one example. And any detected insight is presented in the smart detection area, as well as sent to the customer in an email. The machine learning behind the scenes applies linear regression to decorate the data with additional tags like slope and R-square, and eventually use those tags with a classifying model that picks up the degrading trends. The domain knowledge that I mentioned means that Application Insights is familiar with the semantics of the data and that no configuration or training signal is required from the customer. From this point on, I have a good direction on how to continue my investigation. I can go check if changes were made to the database call, to the database schema, or even data access layer, or I can click here and continue my investigation with Application Insight Analytics, which is a big data analytics tool allowing me to interrogate my data with interactive queries. Authentication in progress. Let's not wait, Arel. Let's continue with analytics.
So let's continue in analytics. So essentially, this is application insights analytics, and as Yossi said, it's a big data query engine that allows you to do interactive queries. Now, we're moving on to another application, which is essentially on a demo website that you have available for you to check out our demos. And we're looking at a real-life example we've added to this demo website. Now, we're looking at a case where requests to my website started prolonging, and I want to know why. So I'm using the analytics query language, which you can see is pretty similar to SQL, only we're using pipes to kind of concatenate the statements. And I'm asking the service to show me HTTP requests that came to my server in the timestamp where in the time frame where I've had the incident. I'm looking only on specific requests that came to my World News website, and I'm asking analytics to summarize and show me the 95th percentile of request duration, break it down by 10-minute beans, and render that as a time chart. Now we can see that it's super fast, and what analytics shows me essentially is that I have a step jump in my request duration. Everything was stable up until 12 p.m. Requests were served in about 1,000 milliseconds, which is 1 second, but then at 12 it kind of jumped to 7 seconds and stayed at that level. Now, analytics also highlights a point in the chart, which it analyzes and found to be a variation point. And now, this is of course very obvious because we only have one spike, but even if we had like a fluctuating chart, analytics would have also found out what are the specific data points I should investigate. And analytics is telling me that I should click the point to get smart diagnostics. So let's click on that and see what happens. So what it does, analytics is running a couple of algorithms behind the scenes, and it found essentially a pattern here explaining the data discrepancy. So it seems like this kind of issue is associated with a specific user segment trying to access or to browse to the sports news page from a specific version of Internet Explorer 11. Now, this is a pretty specific cluster for me to focus at. Also, analytics was kind enough to decompose the duration chart into two separate charts. One is showing me the behavior of duration with the diagnosed pattern, and the other one without the pattern, which stayed stable throughout the incident. So now I know exactly where to focus, and I should probably go and look for any browser code optimization codes that might have been affected or had a regression. Now, the secret sauce behind this is using an in-house machine learning algorithm we've developed. We call it diff patterns. Essentially what it does, it takes two tagged data sets. One data set is tagged as the normal behavior before the incident, and the other one is after the incident or during the incident. And we're kind of doing an analysis and comparison to find what's the difference between them, and are able to produce this kind of discrepancy patterns. Now, this algorithm, diff patterns, is available for you as part of the analytics language, and you can take advantage of it in your manual freestyle investigations, or if you want to do like an automated detection and diagnostic system, that's also available for you.
That brings us to the last demo we have for you guys today. What I want to show you next is how even more complex issues can be analyzed with interactive queries powered by built-in machine learning constructs. Let's imagine that we are all the on-call engineering today, and we've just received a phone call from customer support telling us that in the past few hours, there's been a growing number of complaints about slowdowns in our application. Now, given that that's all we know, a good place to start such an investigation is to examine the duration of HTTP requests for different segments of users and environments. Let's take a look at the analytics query that would help us achieve exactly that. So I'm starting by asking the analytics engine to load the HTTP telemetry for my app. Then I'm filtering the data by the time range provided by customer support. I then define a segmentation key, which is basically a concatenation of the name of the HTTP server that picked up the requests and handled them, the name of the HTTP operation, so I can tell which page in the app or which pages in the app are the ones manifesting those slowdowns, and then some client-side information like the type of client browser and client OS, so I can learn more about the impacted users. And finally, I'm asking the service to compute those average durations for those segments in 1 hour bins, and of course, to draw a nice time chart. Let's run this and see what we get. So it turns out there's over 1,000 such combinations in my data. And as we can see, the resulting chart is chaotic, and none of us can make anything out of it. Now, naturally, what I need is a way to single out only those segments that manifest a clear trend of a performance degradation. Let's see how built-in machine learning constructs in the query language can help me achieve exactly that. So once again, I'm starting with a query that segments my data by 4 dimensions, just the same as before, except this time, I'm converting my data to time series so that I can apply linear regression on the data to produce slope and R-square as new tags in the data. Then I define my own very simple scoring function that I feed to what we can call a mini classifier that would pick up just the 3 segments that manifest the most obvious trend of degradation. Let's run this and see what we get this time. Sweet. So what we can see is that out of more than 1,000 segments, we were able to spot and single out just the 3 ones that manifest the most significant trend of increase or performance degradation. Moving into table view, switching to table view, we can see that there is a lot in common between those segments. We can see that all of them relate to users that use a specific version of Chrome on Linux. So now we know who are the impacted users in this incident. We also see that all of the segments are related to the same HTTP operation. So now we also know which page or pages in the applications are the ones showing those slowdowns. And in fact, we see that the only difference between those 3 segments are the backend servers. We see 3 different names of backend servers that are handling those requests that are slowing down. So that naturally brings up the question, what is going on with these servers? Why are these servers slowing down? Now, perhaps I can try to answer that with telemetry data collected from performance counters. So what I'm going to do now is basically apply the same trick. I'm going to ask the service to do time series analysis for HTTP request telemetry. And then I'm going to do time series analysis with the same machine learning pattern on performance counters telemetry. But this time, I'm going to ask the service to cross-join between these 2 sets of time series by the name of the backend server. Let's run this and see what we get. Sweet. Switching to table view would help us better understand what we found. We basically found that the same 3 servers that were manifesting the slowdowns are also manifesting a very clear increase in the performance counter known as private bytes. Who in the audience is familiar with private bytes, the performance counter? Yeah, lots of folks. So this would be a very clear indication for a memory leak in our application. And in this case, it's also nailing down the root cause for this incident.
That's super cool. So this is just the tip of the iceberg, and we don't have more time to share with you additional stuff. But please do visit the analytics demo website. You have a bunch of queries there with full tutorials, with the examples we've just seen and additional ones that you can check out. So what's next from here? So you're welcome to onboard application insights. It's super easy to get started. We have essentially just add a NuGet to your project or add an SDK. We have SDKs for all available technologies and languages. Check out the machine learning demos in the analytics website. You have the short link here and also the QR for you to scan, and I'll leave it after the presentation. And please feel free to come talk to us at the monitoring analytics booth located right over there. We'll be available for any question or information you would like.
And more demos.
And more demos, of course. We have a lot of related sessions, both breakout sessions coming in the next couple of days. We have another Tech Talk session here at 4 p.m. And we have a bunch of pre-recorded sessions for you to check out. And please complete an evaluation, and we'd like to thank you for your time. And please,
thank you very much.
Feel free to talk to us. Thanks.